Okay, in this video we're going to start section 7.2, volume by the disk method. Up in this course up until now we've found the area under curves, which is two-dimensional, and we've also found the area between curves, which is also, set in 2 dimensions. In this section here we're going to jump into 3 dimensions, and how we're going to do that is take these flat plane surfaces that we have been finding in the past, and we are going to rotate them around an axis of rotation. Sometimes that axis of rotation will be the x-axis, so we're going to rotate, this flat two-dimensional plane region here around the x-axis, and in this case it would create sort of like a bubble shape or an egg shape. So we're going to start finding volume, and first we're going to look at the disk method, and next we'll look at the washer method, and then third will be cross sections. So let's get started. You've already learned that area is only one of the many applications of the definite integral. Another important application is the use in finding the volume of a 3D solid. In this section you will study a particular type of three-dimensional solid, one whose cross-sections are similar. Solids of revolution are used commonly in engineering and manufacturing. Some examples would be vehicle axles, funnels, pills, bottles, pistons that go in engines. If a region in the plane is revolved about a line, the resulting solid is a solid of revolution, and the line it's revolved around is called its axis of revolution. The simplest such solid is a right cylinder or disk, which is formed by revolving a rectangle about an axis adjacent to one side of the rectangle. So here in the picture we have our rectangle, and we're going to use capital R for the height, W for its width, and just like the description said, this rectangle is adjacent on one of its sides to the axis of revolution. So when we start to spin this rectangle around that axis, it's going to form a disk. So the volume of such a disk is the area of the disk times its width. Well, what is the area of the disk? Well, it's just the area of a circle, pi r squared. The width of the disk is w, so pi, the radius squared, w. To see how to use the volume of a disk to find the volume of a general solid of revolution, consider a solid of revolution formed by revolving the plane region in figure 7.14 about the indicated axis. So here's figure 7.14. We got this curve going on here above our axis of revolution. Here is our representative rectangle. We have a rectangle under the curve, height r, width delta x. And we're looking at this function from x equals a to x equals b. So we revolve that plane about the indicated axis. To determine the volume of the solid, consider a representative rectangle in the plane region. When the rectangle is revolved about the axis, it generates a representative disk whose volume is. So here is our rectangle, height r, width delta x. We rotate that around this axis of revolution. And our change in volume, our delta V, or the volume of each individual disk, is pi times r squared, the radius squared, times its thickness, delta x. Approximating the volume of a solid with n such disks of width delta x and radius r of x sub I produces this summation of the volume of the solid. I equals 1 to n disks, pi r squared delta x. And because pi is a number, constant multiple rule, we can pull that pi out in front of our summation symbol and get pi times the summation of r x sub I squared, the radius squared, times delta x. So here we have an approximation with 1, 2, 3, 4, 5, 6 disks, and of course we're going to cut those into thinner and thinner slices. The more disks we have, the better our estimation. We can slice them so thin they become infinitely thin. So this approximation appears to come better as our norm approaches 0, or as n approaches infinity. The number of the disks becomes infinite. So we can define the volume of the solid as, here's our summation notation, and we translate this into our calculus notation. The pi stays out front. The summation becomes our integral sign from a to b. Here is our radius squared, Rx quantity squared, delta x becomes dx. So we started with the volume of a disk, a simple pre-calc or even geometry formula, pi r squared times its width. We had the representative element. Remember, representative element, that is big in the next two sections. Our representative element was a rectangle underneath the curve. The volume of each rectangle is delta V, or the change in volume of the whole region is pi r squared delta x. And we turn that into our new integral formula. Pi, the integral from a to b of Rx quantity squared dx. So a similar formula can be derived if the axis of revolution is vertical. So here we've been talking about a horizontal axis of revolution. It's nice if that happens to be the x-axis. Here in the picture, it's our x-axis. We're rotating around it. So our volume is pi, the integral from a to b, of r of x squared, that's our radius, or the height of the rectangle, and we are integrating with respect to x, delta x, and that is also the width of each rectangle. The rectangle has a width of delta x. That is the variable that we are integrating with respect to. And also note that the representative element, this rectangle, is perpendicular to the axis of rotation. We can also do this for the y-axis. Maybe we want to revolve some shape around the y-axis. Well, now we are integrating pi times the integral, and we just change the letters from c to d. These are numbers on the y-axis of r of y squared. So here now we are perpendicular to the y-axis. And here is the height of our representative element, r of y, and the width of the rectangle is delta y. And that tells us our variable is dy. We're integrating with respect to y. So let's dive in, have some fun with example 1. The simplest application of a disk method problem involves a plane region bounded by the graph of a function f and the x-axis. If the axis of revolution is the x-axis, then the radius, capital R of x, is simply our function, f of x. So in example 1, we're going to find the volume of a solid formed by revolving the region bounded by the graph of our function f of x is equal to the square root of the sine of x and the x-axis between 0 and pi. So here is our two-dimensional picture of our function. Our function is the square root of the sine of x between 0 and pi, so we have this little like half of an oval going on. And the height of a rectangle, no matter where we draw it under here, we can have a real short one way over here to the left. In the middle, we'd be at our maximum height. Whatever the height of that representative rectangle is, that's r of x. That is our radius, which also just happens to be f of x. And then what we're going to do is take that flat plane region and spin it around the x-axis. So it's going to form sort of this egg shape. And we'll find the exact volume of that egg. So, since we're starting here with something brand new, let's write out the formula. Volume is equal to pi times the integral from a to b of our radius, r of x, squared dx. So that's our generic formula. Let's plug in what we have in our problem. So pi is still pi. We are integrating from 0 to pi. And then we have our radius squared, which in this case again is just our function, which is the square root of sine x. Square root sine x is our function and our radius, and we're integrating with respect to x. But before we integrate, let's try to clean this up and simplify it a little bit. We have a square root and a quantity squared. Those are inverse operations. If we square and square root something, we're back to where we started. So we lose the square and the square root, and we just have sine of x dx. Alright, this will be a nice simple integration. So we have our pi out front. And the antiderivative of sine x is negative cosine of x. And we are evaluating between 0 and pi. So now time to evaluate that. Upper limit goes first. pi is going to jump in the place of our variable. And don't forget this pi out here. When we multiply that through, it's going to be distributed across everything of our evaluation of the definite integral. So we're going to start out here with negative cosine of pi, and then subtract our lower integral, or our lower limit. When we plug the 0 in, we get negative cos of 0. Negative cos of 0. So we'll work in the brackets here, and then we'll multiply by pi at the end. So it looks like we're going to need a little unit circle action. Our angles are 0 and pi radians. So 0 radians would be here, pi radians here. And the point of interest would be 1, 0 and negative 1, 0. So the pi is still outside. And we have negative cos of pi. Well, what's the cos of pi? It's the x value at pi radians, or negative 1. Minus negative cos of 0. What's the cos of 0? Positive 1. So we're going to have some double negatives. Minus a negative becomes a plus. Minus this negative also becomes a plus. So inside those brackets, we're going to have 1 plus 1, or 2. And then outside the brackets, we have our pi. So here in the brackets is 1 plus 1. Pi is out front, so we get 2 pi. So what is the volume of this egg-shaped 3D solid? 2 pi units to the third power, units cubed, whatever those units happen to be. So this is a nice example, and again, our axis of rotation was the x-axis. So the radius that we were spinning around the x-axis, our representative rectangle, also just happened to be our function f of x. That's not going to happen in example 2. So in example 2, revolving a line, or about a line that is not a coordinate axis. Find the volume of the solid formed by revolving the region bounded by, here is f of x, 2 minus x squared, and g of x, that is just a horizontal line at y value of 1, and we are going to rotate that about the line y equals 1. And this is summed up nicely in the picture. On top is our two-dimensional representation of the area under the curve. So when we were finding area under the curve in the previous section, earlier, what was that, chapter 6, or no, chapter 7, when we were just thinking about this as the area under the curve, we did upper function, the function that was higher, minus the lower function. And we're still going to need to do that here. Because remember, we need a representative rectangle that exists between these curves. And what tells us the height of that representative element at any point along the x-axis is the upper function minus the lower function. And let's see, they do give away in the picture here. You know, we are going to integrate from negative 1 to 1. If the picture did not accompany this, you could figure out, okay, where do the graphs intersect? When do we begin and end our definite integral here? Well, we would just take our functions and set them equal. 2 minus x squared is equal to 1. And then we'd get everything on one side, and we'd get x squared minus 1 equals 0. And then we'd have x squared equals 1, or you could factor this into x plus 1, x minus 1. Either way, when you square root this here, we'll get plus or minus 1. So the x values where our two curves intersect are at negative 1 to 1. So that is where our upper and lower limits of our integral will be. So, what is our radius? Remember, our radius is capital R of x. And again, think back to the last section. How would we find the area under the curve? Well, it's going to be the upper function, and in this case, that's f of x, minus the lower function, which is just a horizontal line, g of x. So let's find what the radius is going to be in terms of x. The radius in terms of x is going to be, well, f of x was 2 minus x squared. And we're going to minus g of x, and g of x was just 1. So, you know, we can just disregard the parentheses, knock those right out of there, and let's collect our like terms. So we're going to have 2 minus 1 is 1 minus x squared. That's supposed to be a 2. So the radius, r of x, of this 3D solid is going to be represented by 1 minus x squared. So that is our radius. So, again, because it's pretty new, I'll rewrite out the whole formula. It's going to be pi, the definite integral from a to b, of our radius squared, pi r squared. You know, the pi's out front, here's our r squared, and we are going to integrate with respect to x. So, what do we know in this problem? Well, our lower limit's -1, our positive limit, or our upper limit is +1. Our radius that we're going to square is 1 minus x squared. And we're going to integrate with respect to x. Oops. So, we have, it looks like an inner function, a quantity squared. Can we integrate that with like a reverse of the chain rule? Our inner function is 1 minus x squared. That inner function's derivative would be -2x. Do we have a -2x dx for a du substitution? No, we don't. But we still can integrate. What we have here is a binomial squared. Let's FOIL it out. If we do FOIL that out, we're going to get 1 minus 2x squared plus x to the 4th dx. So now we can integrate. The antiderivative of 1 is going to be x minus, this would be raised to the power by 1 divided by the new power, 2x to the 3rd over 3 plus x to the 5th over 5. And that is a definite integral we will evaluate between 1 and -1. So the actual running our upper and lower limits through there, the evaluation of this integral is not going to be bad because we have 1s and -1s. So we have our pi out front, and we drop a 1 in wherever we see an x. So we're going to first have 1 minus 2/3 plus a 5th. And then we are going to minus the lower limit ran through there. And then at the end, we'll distribute that pi through it all, or just collect what's inside the brackets and multiply by pi. So plug the -1 in. This x becomes a -1. This x to the 3rd will become a -1 times 2/3 will be a -2/3, which will hit this negative, and that'll become a positive 2/3. And we plug the -1 in here. A -1 to an odd power is a -1. So that'll overpower this positive and become a -1/5. And if we work just within the brackets, get a common denominator, distribute this negative, collect up everything, we're going to get 16/15, and then times pi. Units to the 3rd power. So we found our flat plane region. Oops. You know, here was our plane region. We determined sort of like the area between it, upper function minus lower, to get our radius. And then we spun that plane region around the axis of rotation, which happened to be y equals 1. And we get this sort of egg-like shaped looking thing here, our solid of revolution. And its exact volume is 16/15 pi units to the 3rd, units cubed. So there are two good examples of the disk method, one where our axis of rotation is the x-axis, the other one where we're rotating around something that is not the x-axis. And now this brings us to the washer method. The disk method can be extended to cover solids of revolutions with holes by replacing the representative disk with a representative washer. You know, a washer is just a disk with a hole in it. The washer is formed by revolving a rectangular solid about an axis, as shown in the figure over here. If lowercase r and capital R are the inner and outer radii of the washer, and W is the width, we get the following volume. Let's look at the picture here. You know, here is our axis of revolution. Our rectangle is not touching it. So when we spin it around that axis of revolution, we will have a hole in the middle of the disk. And we get a nice 3D pic of that here. The top of the rectangle is capital R, our upper radius, or our higher radius. The bottom of the rectangle is lowercase r, or our lower radius, inner radius. So what would the volume of this disk be? Well, it's going to be pi r squared, and then we're also going to minus out this lower radius squared. So it's going to be pi times the quantity, bigger radius minus smaller radius, times the width of the disk. To see how this concept can be used to find the volume of a solid of revolution, consider a region bounded by outer radius, capital R of x, inner radius, lowercase r of x, as shown in figure 719 down here at the bottom. If the region is revolved about its axis of revolution, the volume is represented by, we have pi, the integral from a to b, outer radius, capital R of x squared, minus inner radius, lowercase r of x squared, integrated with respect to x. If we look at the picture, here it looks like a straight line is the upper radius. So that hits the top of the rectangle. That is our capital R of x. The lower curve hits the bottom of our representative rectangle, and that is lowercase r of x. So capital R of x minus lowercase r of x, both of those are squared separately. Outer radius squared minus inner radius squared. Do not subtract the radii and then square that difference. And then we take this odd-shaped piece here and we spin it around our x-axis, and we get this cone-shaped solid of revolution. So let's use the washer method here in example 3. Find the volume of the solid formed by revolving the region bounded by the graphs of square root of x and x squared about the x-axis as shown in the figure. So we're here between 0 and 1 on the x-axis and 0 and 1 on the y-axis. Of course, these two functions are going to intersect at 1, 1. So the square root function starts up steep and then starts to taper off. The x squared function starts out slowly and then starts to accelerate. So here, and we can just tell by the picture, that the square root of x is our upper function, and the x squared function is our lower function. So let's write this out. We have our outer radius, r of x, capital R of x. The outer radius is the square root of x function. Lowercase r of x. Lowercase r of x. The inner radius is our other function, y equals x squared. So this new formula here for the washer method is volume equals pi. We integrate from a to b, and then we have capital R of x squared minus lowercase r of x squared dx. And I guess I could have brackets around there for that dx. So outer radius squared minus inner radius squared, that definite integral from a to b, and we multiply by pi. So let's plug in the one specific to our problem. Volume equals pi, and we are integrating from 0 to 1. Our outer radius, capital R of x, is, we're going to take whatever that is and square it, and we're going to minus our inner radius, or lowercase r of x squared. Our outer radius was square root x. Our inner radius was x squared. Give me a little room there so I can throw my dx at the end. And we need a bracket there. Alrighty, let's see if we can simplify that a little bit and do our integration. So we still have our pi, integrate from 0 to 1. Square root squared cancels. So here we're just going to have an x minus x squared quantity squared is x to the 4th dx. That should be easy enough to integrate. We're going to have pi. The antiderivative of x to the 1st is a half x squared, or x squared over 2. This becomes x to the 5th over 5. And we evaluate that from 0 to 1. Ooh, I like to see zeros in my upper and lower limits. So we start by plugging in our upper limit 1. That 1 is going to hop in there, and then we're going to have pi. And then when we drop this in, we have 1/2 minus 1/5. And then we subtract our lower limit run through, and this is why I like 0 so much. We plug in 0 and get 0 divided by 2 is 0, 0 divided by 5 is 0. That becomes just a great big nothing. So we get pi times 1/2 minus 1/5. 1/2 minus 1/5 is 3/10 pi.